3, 2, 1. Here we go. Okay, momentum. We need to revisit Newton's second law. Okay, Newton's second law we all know as F, or the net force, equals the mass times the acceleration vector. However, I lied to you. Wow. Well, I didn't lie to you. I just didn't tell you the whole truth. Okay. Yes, this is Newton's second law. This is the most common use of Newton's second law. However, this is not what Newton put forth in the Principia Mathematica when he decided to go ahead and invent calculus so that he could invent physics. It's not there. So we're going to imagine this. Okay. We've got this ball here. This is it has mass 1, so this is ball 1. All right, ball 1. Okay, and then over here we have a... Oh, I lost my color. Where'd the color go? Shoot. I liked it. All right, good. And over here we have ball 2. And then we have ball 2 is over here. All right, ball 1 is traveling. It's going this way with an initial velocity. Okay, for ball 1, this has mass 1. Okay, ball 2 is traveling this way. Okay, with the velocity 2, and it has a mass 2. Now, we will be getting more into specifically why this happens, but these are two massive objects. Let's pretend that they are massive, massive objects. They will be stars. These are stars out in space. Really freaking big things. Okay? And if they're really massive, then they will have a gravitational force towards each other. And one will experience a massive force towards 2. Okay, and that will experience the force of the second object on the first. And 2 will experience, according to Newton's third law, will also experience an equal and opposite force, okay, that 1 will be exerting on 2. So we have these two objects. And for our intents and purposes here, this is our system. Okay, is this whole thing here. Okay, now, this could very well be atoms. Atoms experience a very similar thing, except atoms could be attracted by an electrical force, okay, over a very short scale, and they could behave in very much the same way. But if it's stars, then it's going to be gravity, and they're not. They tend to be neutrally charged, roughly, or the slight plus, 3,000 minus 3,000 charge that a star would have is not anywhere near significant enough to move it towards the other star. Gravity is what it's going to need. So, according to Newton's third law, we know that the force of the second object on the first is equal to the negative of the first object on the second. Well, I'm going to play around with this a little bit. And we know that F of 2, 1 plus the force of 1, 2 is going to equal 0. Yeah? We should be okay there. Well, then we're going to break this down a little further. All right, so we're going to take that. In fact, I'm going to select it and move it. Okay. Move that down here. Okay, so that this is the same thing as m1 times the acceleration of 1 plus m2 times the acceleration of 2 is equal to 0. Yeah? But what else what is acceleration? What do we know acceleration to be? Okay, think it's what? It is the rate of change of velocity. So we, being good, dutiful calculus students, we can rewrite this as m1 d dt of v1 plus m2 d dt of v2. And this will still equal 0. Yeah? Okay. Well, another way of looking at this, though, is that this ddt is the operator, and the masses are constant. I hadn't assumed that yet. Assume the masses are constant. Okay, so we can rewrite this whole thing as ddt of m1 v1 plus ddt of m2 v2. But even so, and we can, and this will still equal 0. Does equal, I don't want to put does not equal, does equals 0. All right, and we can even take this the next step further. Because this is a system, we separated them up here before, but we kind of had them together, so this could also still be m1 v1 plus m2 v2 is going to equal 0. Okay? Now, and we know that, because the sum of the derivative equals the derivative of the sum, right? We're okay with this part. Okay. Right. Well, what happens when the time derivative of something equals 0? Okay. Or if the time derivative is 0, that means it's constant, right? So this is the rate of change of this value plus this value equaling 0 means that whatever this amount isn't going to change over time. That this means that this value right here is conserved. That whatever change it goes through, whatever change one has, is going to be opposite of the change of the other one. Okay, which brings us to, well, what is this value right here? This m times v, okay, or mass, times velocity equals momentum. Okay, and this is the amount of momentum something has. And as we just see with this, the momentum of something, or the momentum of a system, is always conserved. Okay, that the change, if there's no external, it's the same things apply. With no external forces, okay, that the momentum of a system, the force that one exists on the other, will change they will change each other's momentum. Okay, in equal and opposite ways. Okay, so we've got this new term, we call it momentum. What can we call it? Well, we've got m for mass, we have v for velocity, we have a for acceleration, we have w for work, we even have p for power. What are we going to call momentum? Well, momentum, okay, because all the cool letters are taken, okay, in the infinite wisdom of those of us that do physics, we decided to give it one of the only remaining letters that doesn't really have anything attached to it, and that is P. Lowercase p. Even power is roughly uppercase P. Sometimes they use it. Usually they just write the word power. Okay, so P, lowercase p, is our momentum. Okay, it is defined. Okay, actually I prefer to think of it as being, it is named P after P-Dog, but unfortunately I can't lay claim to that because it was P long before P-Dog came along. P is defined as, our momentum is defined as mass times velocity. Okay, it has units of kilogram, meters per second. Kilogram meters per second squared, we call those newtons. Kilograms meters squared per second squared, we call those joules. What is a kilogram meter per second? It's a nothing. It's nothing. Okay. Yeah. Well, I actually like calling it a mo. Okay. It's a mo. Hey mo. But it has nothing. It is kilogram meters per second. You will sometimes see it, and this is a hint as to where we will be going in the near future, as a Newton. A Newton second is another way of seeing this. But this is actually this is something for something. These are units for something that is slightly different. I like it better because it's not a fraction, and I hate fractions. All right, so if mv equals p, we now have the time derivative of p1 plus p2 equals 0. Or, okay, if we have an isolated system, or if there's no external force, then we have the total initial momentum of a system equals the total final momentum of a system. And this is a constant. The value of the momentum of a system is constant if there are no external forces acting upon it. Okay, so let's come back over to our drawing here. These two are experiencing a gravitational force towards each other. The change in momentum that one experiences is going to equal and be opposite to the change in momentum from the other one. Okay, if there are no external forces. If all of a sudden one of them sprouts a rocket and starts firing it off in one direction, it's going to have a slight effect on the other one because of the gravitational force. But there will be an external force on the system. And the momentum, well, actually, no, that's not entirely true. That's really a bad explanation there. If there was an external force to come in here and move one of the stars independently, that would change the total value of the momentum of the system because it would be an external force. If they were all internal forces, okay, all their gravity and everything happening just within our system, there will be no change in the momentum. Okay, so that's the next thing here. Momentum is conserved in an isolated system. Okay, this is a law. You will find that this is one of the most powerful devices, way up there with work of non-conservative forces equals delta E. This is way up there. Okay, the momentum is conserved. The momentum you have to begin with is there when you finish, regardless, always for an isolated system. And if you consider that the entire universe is isolated, okay, all the momentum that has ever existed from the Big Bang until now has been conserved. Okay, everything that is moving right now, okay, has an equal and opposite motion and has changed the momentum of something else, okay, since the beginning of time. Now, we are assuming something. We are assuming that there is no external force outside of the universe that may be helping out a little bit or taking stuff away. But we don't know about that. We have no observance of that, so we don't bother with that. All right. So what if it isn't isolated? Okay. What if it isn't isolated? Let's come back up here to our. Let's come back up here. What if this isn't isolated? What if we take this right here? What if we take object 1 to be our system? Is object 1 isolated? No, it is not. Why? Because it has the force of 2 acting upon it. The force of 2... That's okay, Sean. Happens to the best of us. Okay. So, Object 1 has an external force acting upon it, therefore it is not isolated. The two of them together, these are the only things around, the two of them together are an isolated system. So isolated systems are defined as those with no external force. All right. So let's look then at the rate at which momentum changes. So let's go back to this. So let's draw a circle here, and let's get a little more shade. All right, throw a little shade on this. Okay, here is our mass 1 again. Let's. All right, I'll have to show you guys pictures of my Halloween costume because it was pretty rocking. All right, here this is mass. Has mass of m. It's got a velocity in this direction, and it is experiencing a force this way. Okay. All right. The change in our momentum with respect to time equals, okay, d of mv dt okay, which will equal, now if we have to do this chain rule here, we're not holding either one of them, neither one, the product rule I mean, neither one of these are constant. We're not assuming. So this is going to be mdv dt plus dm dt times v. Now here's a little, and that's still a vector. Okay. This dp dt, okay, is the time derivative of our momentum. This, then what? I mean, what is dv dt? It's our acceleration. Oh, we come back. Mass times acceleration. Okay, and over here, this is called, has a dot over it. It is called the mass flow. It is the rate at which mass travels. Okay, or the rate at which mass changes is the mass flow. Okay, so, or the mass flow rate. This, of course, equals our net force. These are the sum of the forces acting upon an object, and so we have our final equation here of F net equals dp, should be lowercase, dt. And this, my friends, is the whole truth. This is what Newton put into his Principia Mathematica, was the net force on an object is what causes the rate of change of its momentum. Okay, and momentum is the state of motion of a massive object. Okay, is a way of thinking about it. So this is the force is the rate of change of the state of motion of a massive object. Is how he referred to it in the Principia. And this is the truly powerful part of, this is Newton's true second law, is F equals dp dt. Now, in most situations, in the vast majority of situations, this is zero because your mass doesn't change. So you're just left with mass times acceleration. However, there are a couple of situations that you guys may be able to think of where it does change. Okay, want to give it a shot? In what situation are you going to have a force that results from a change in mass, not a change in, not the concept? Corey?
A rocket burning fuel.
A rocket burning fuel is my favorite example. There's another one that may be even more common and something you can test out at home.
Balloon.
Okay, a balloon is one of them. Yes, excellent. A balloon. You blow up a balloon and you let it go, and poof, it shoots air out. Well, How is it accelerating? Because it's shooting mass out the back of the balloon. You guys ever seen firefighters in action? Okay. Have you ever seen them? Have you ever seen one guy try to hold the hose? Okay. I'll give you. No, you haven't seen one guy try to hold the hose, because the hose will blow him back off of the street. Okay. They actually have to angle it up. Okay, to increase their normal force into the ground so that the hose doesn't push them away. They angle it up because the force of the water coming out of the hose, okay, is enough to push him into the ground, and it increases his normal force. If he were to angle it down, okay, he decreases normal force, and he might actually go airborne with the pressure that's coming out of a fire hose. Sounds like awesome. Now, if one of the if the fireman lets go, okay, it's like one of the first rules: do not let go of the fire hose. If you let go of the fire hose, it will start to whip around, and it can kill people with the force of the whipping of the fire hose. So, okay, so those are, so rockets, the blown up balloon, okay, fire hose. Okay, both of those, all three of those are examples of our mass flow in action. A garden hose does the same thing. If you hold a garden hose and you put a nozzle on the end of the garden hose and you fire it, okay, you're shooting water out one way, you feel it the other way, you feel a push back. That's the same thing on a much lesser scale. Okay, so yes, you can try this at home. Guys, go water the lawn.